We previously established that the Inertial Navigation System, or INS, starts from a known initial position and, by continuous measurement of aircraft accelerations, keeps updating itself to the present position. We also said that it gives a great deal more information than just a present position, latitude and longitude. The accelerations are detected by a device known as an accelerometer. They are then converted, firstly into velocities, and secondly into distances gone by integrators. We are now going to examine this measurement and integration process more closely. We'll start by looking at accelerometers in a bit more detail. There are various different forms of accelerometer, but a popular early model was the pendulous E and I bar type. The E and I bar is a fairly common form of transducer, and is also found, for instance, in the servo-assisted altimeter, which you have already studied. The E bar is made of a material with a high magnetic permeability. This means that it responds by producing a high magnetic flux density in proportion to the inducing field, and responds rapidly to rapid changes in the inducing field. A source of primary current is applied through a coil winding round the centre leg of the E-bar. If it were DC, this would convert the bar into an electromagnet, with a static north pole at one end and a south pole at the other. However, the primary exciter source is AC, usually at 400 Hz, and so the effect is that the magnet changes polarity every 400th of a second, that is, north to south and back to north again. Secondary windings on the outer two legs of the E-bar therefore experience a change of magnetic flux and pick up secondary AC voltages, the same principle as a transformer. The amount of induction in the secondary legs is affected by the gap between the E-bar and the I-bar. The I-bar is attached to a rigid pendulum and hangs vertically when there is no lateral acceleration. If the gap is the same, then the amplitude of the voltage induced at the two ends will be identical. But the polarity will be opposite, because when one end is a north pole, the other is a south pole, and vice versa. The positives and negatives cancel each other out, and we get a resultant of 0. However, if the whole accelerometer now experiences an acceleration, in this example to the right, the pendulum will swing to the left. Now the gaps at each leg of the E-bar are not the same, because the I-bar has been displaced. Therefore the induction at each end will be different. This will affect the amplitude, but not the polarity or phase. The positive and negatives will no longer cancel out, and there will be a resultant, which will be a new sine wave. This secondary induced voltage is passed to a feedback amplifier, where it is amplified, phase detected and rectified to DC. The DC is then passed to solenoids, which act as electromagnets, and attract a permanent magnet in such a sense as to recentralize it. A voltage is picked off and measured downstream of the amplifier. This voltage will be proportional to the restoring force, and therefore the initial acceleration. By measuring the amplifier output voltage, we have a measure of lateral acceleration. Although the principle of the pendulous E and I bar accelerometer is as described, the actual mechanization does not need a long vertical bar, and practical accelerometers are usually a rectangular shape, with the long side horizontal. We will represent them like this in future diagrams. Integrators convert a rate of change over a period of time into total amount of change over that time. If the input is acceleration, which is a rate of change of velocity, then the output is change of velocity. If the input is velocity, which is a rate of change of position, then the output will be change of position, which is another way of saying distance gone. Most modern INS integrators use digital computing. Suppose that over a second the output from the accelerometer is an analog voltage like this. The integrator digital sampler will turn it into this. The input of acceleration, for example, is sampled many times per second, and each instantaneous value is multiplied by the time interval between samples. Adding all of these multiplied values together gives the total increase in speed over 1 second. Integration is a process of successive minute additions to, or subtractions from, the last known value to create a new value, in very small increments, but very frequently. We use 2 accelerometers in INS. They are mounted in such a way that one is always kept pointing towards true north. When its accelerations are integrated and processed, we get latitude. The other one is kept pointing true east. When its accelerations are integrated and processed, we get longitude. The accelerometers are mounted on a table that can rotate, called a platform. The platform is shown, obviously out of scale to the aircraft, for the sake of clarity. Suppose the aircraft is initially flying north. The orientation of the platform and the accelerometers will be such that the accelerometers have their sensitive axes facing north and east. Now suppose that the aircraft alters heading 45 degrees to the right. The platform servos have to turn 45 degrees to the left with respect to the airframe. The result is that the platform remains orientated to the north. This is one of the corrections to the platform for aircraft maneuvers. There are also corrections for pitch and roll. If, for instance, the airframe is pitched 5 degrees nose up, the front of the platform must be driven 5 degrees downwards with respect to the airframe. If the left wing is dropped, the platform must be driven upwards on that side to keep it level with the ground. The platform has motors in pitch, roll and yaw. For the INS to work, the response and correction to any sense manoeuvre has to be near real time, and the accuracy has to be better than 1/10 of a degree in all 3 planes. Additionally, the platform, which contains 2 accelerometers and 3 gyros, is quite heavy. The design of the platform servos was a demanding engineering challenge. Because of their mechanical complexity, the early platform servos had a limited mean time between failures. This was one of their known weaknesses, and it is one that has been overcome in the later inertial reference system. The information flow in INS is organized into 2 channels, a north-south channel and an east-west channel. Each accelerometer senses accelerations, one in the north-south sense. These accelerations are labelled A subscript n here. If the aircraft accelerates southwards, that is simply a negative north acceleration. The other accelerometer senses its accelerations in the east-west sense, which are labelled A subscript e here. If the aircraft accelerates westwards, that is simply a negative east acceleration. The northerly acceleration passes through the first stage integrator, where it is integrated into velocity northwards, v. You might think that if we have used the convention A subscript n for northerly accelerations, to be consistent, we should use v subscript n for northerly velocities, but we don't. In navigation, v on its own usually means northerly velocity, and u on its own means easterly velocity. It is a widely used convention, and we will follow it. The easterly acceleration is converted by its integrator into velocity eastwards, or u. These velocities will be integrated again shortly into distance gone, but even at this stage we can use them to get track and ground speed. The north and east velocities are passed to a compounder. A compounder is simply a computing device for taking velocities which have been resolved in 2 directions at 90 degrees to each other and calculating a resultant. Suppose, for instance, that we are in a jet airliner, and our northerly velocity, v, is 387.3 knots, and our easterly velocity, u, is 216.8 knots. Then our vector diagram is like this. Although we carry out addition of 2 vectors, the aircraft does not travel first north, then east. What happens, of course, is that it is flying up the resultant, and the resultant of v and u is the vector of track and ground speed. The problem is solved using elementary trigonometry, finding the track from the tangent, which is given by u over v, and finding the ground speed by Pythagoras. This sort of fairly simple calculation can be performed using only calculator-level technology. There is no complex computing involved. Typically, this would be carried out several times a second and continuously refreshed on the display, so it would seem to the pilot to be continuously calculated. In this example, we have a true track of 029.3 and a ground speed of 444 knots. The velocities are also passed forward to a second-stage integrator, where they are converted into distance gone, or displacement north and displacement east. These are labelled S subscript n and S subscript e in the picture. It is necessary for the initial position to be input into an INS before use, so that the system knows where it is starting from. The relationship between nautical miles and change of latitude is a simple one. 1 minute of change of latitude is 1 nautical mile, anywhere on the Earth. 1 degree of change of latitude is 60 nautical miles. So suppose that, in this example, the start position were 5137.3 north, and you had flown 20.5 nautical miles northwards. Your SN value of 20.5 minutes change of latitude would be added to the start latitude to give a present position of 5157.8 north. This means that you have a continuous readout of your present latitude, in just the same way as the tripometer on your car continuously tells you your present distance along a route. Longitude is slightly more complicated, because 1 minute of change of longitude is 1 nautical mile only at the equator. You can see that the distance on the Earth at latitude B, between the same change of longitude, is less than it is at latitude A, the equator. This east-west distance on the Earth is called departure, and is measured in nautical miles east or west. The equation linking departure and change of longitude is that change of longitude in minutes equals departure over the cosine of latitude. However, there is a mathematical function called the secant, which is simply the reciprocal of cosine. For instance, the cosine of 60 degrees is 0.5, so the secant will be 1 over 0.5, which is 2. So we can rewrite the above formula as change of longitude in minutes equals departure times secant latitude. This gives us a computing method for calculating the change of longitude. SE is coming out of the second stage east-west integrator. SE is nautical miles in the east-west sense. This is departure. We therefore take this departure and multiply by the secant of latitude. Present latitude is already available to us, so the system takes a pick-off latitude from the North Channel and feeds it to a microprocessor, which calculates the secant and multiplies it by the output of the east-west second stage integrator, thereby converting the departure into change of longitude. Let's just sum up that data flow again, because we are going to use it to build on in a future lesson. We have a north and an east accelerometer. They sense every change of aircraft movement and pass it to first stage integrators. The first stage integrators continuously add up these accelerations, thereby converting them to velocities. The velocities are used to calculate track and ground speed, and they are also passed to second stage integrators, where they are converted to distance gone. The northerly distance gone is simply added to the initial position to generate a new latitude. However, the easterly distance gone has to be converted to change of longitude. We need an input of latitude. Fortunately, we already have it. It is the current latitude part of present position in the display. The latitude therefore passes to a secant multiplier. This converts it to change of longitude, which is added to the initial position to generate a new longitude. Because of the speed at which computers operate, this process is repeated many times a second. We therefore have a continuously updated present position. Let's summarize the whole lesson now. There are various different forms of accelerometer, but the pendulous E and I bar type is a fairly common one. The actual mechanization does not need a long vertical bar, and practical accelerometers are usually a rectangular shape, with the long side horizontal. Integrators convert a rate of change over a period of time into total change over that time. It is essential that the accelerometers are mounted on a table that can rotate, pitch, and bank, called a platform, in order that they can be kept pointing north and east. The platform servos have to be rapid response and very accurate, and the platform is heavy. This is difficult to engineer. Consequently, the servos used to wear out quickly on early models of INS. Finally, we covered the data flow from the accelerometers to the display. That concludes this lesson. The next one will cover platform stabilization.